Hello, and welcome to the Deep Dive.
Great to be here.
Today we're tackling something fundamental, computer architecture.
That's right. It's really the invisible blueprint behind, well, pretty much all the tech we use.
Exactly. From your smartphone to massive data centers. It's everywhere, but you don't often, see it. Still, absolutely critical.
It really is. The design choices made here dictate so much about what technology can actually do.
So, our mission today is to unpack this. We've done our research, looked at the core principles, and we want to pull out the key insights, give you a clear understanding of how computers really work, especially now in 2025.
We'll be looking at the CPU, the processor itself, then how memory is organized, that memory hierarchy idea.
And also that instruction set architecture, the ISA, plus the tricks engineers use to make things faster.
Performance enhancement techniques, yeah.
Yeah.
Pipelining, parallelism, all that good stuff.
Think of this as your quick way to get properly informed about this foundational tech. So let's just jump right in. The big question first. What exactly is computer architecture? And maybe more importantly, why should we care about it?
Okay, yeah, good place to start. Fundamentally, computer architecture is the set of rules and methods that describe how a computer system is put together and how it functions. It's the blueprint.
The blueprint, okay.
Yeah, it defines the major components, CPU, memory, how they talk to each other, how they're organized. And crucially, it defines the language the hardware understands, the instruction set architecture, or ISA.
So it dictates how hardware and software interact.
Precisely. It is the interface between hardware and software. And why care? Because architecture directly determines what a computer can do, how fast it can do it, how much power it uses. Everything from battery life on your phone to, the power needed for training huge AI models in 2025. It all comes back to architectural choices.
Wow, so it's not just for chip designers then?
Not at all. Anyone who develops software needs some grasp of it to write efficient code. Anyone managing IT systems needs it. And really, for anyone curious about the tech that shapes our lives today, understanding the basics of architecture is, I think, pretty essential. It affects performance, energy, cost, everything.
That makes a lot of sense. Okay, you mentioned the CPU, calling it the brain. Let's dive into that. What are the main components inside a CPU?
Right. The CPU, the central processing unit, it's the engine that runs the programs. We can break it down into three main parts. First, there's the arithmetic logic unit, the ALU.
ALU.
This is where the actual number crunching and logic happens. Addition, subtraction, multiplication, and also logical operations like A and D or not T. It's the computational core, the workhorse.
Okay, the calculation part. What's next?
Next up is the control unit, or CU. If the ALU does the work, the CU is the manager, the director. It fetches the instructions from memory, figures out what they mean, that's decoding, and then generates all the control signals to make other parts do their job. Tells the ALU what to do, manages data moving between registers and memory. It runs the whole show, coordinating that instruction cycle we'll talk about.
The conductor of the orchestra, kind of.
Exactly. A good analogy. And the third key piece.
Yes.
Registers. These are small but incredibly fast storage locations right on the CPU chip itself.
Like tiny bits of memory.
Tiny bits of very fast memory, much faster than anything else. They hold the data the ALU is actively working on right now, the instruction that's currently being processed, the address of the next instruction to fetch, that's the program counter or PC.
The PC, right.
And other temporary results or status flags. Their speed is critical. They give the CPU immediate access to the data it needs most urgently.
Okay. ALU for calculations, control unit managing things, and registers for super fast, immediate storage. So how do they work together? You mentioned the instruction cycle.
Yeah.
How does the CPU actually run a program instruction by instruction?
Right, the instruction cycle. It's the fundamental sequence the CPU repeats for every single instruction managed by the control unit. It starts with fetch.
Fetch.
The CU fetches or retrieves the next instruction from memory. The address of that instruction is stored in the program counter, the PC. So the PC always points to the next instruction needed.
Got it. Fetch the instruction using the PC address. What then?
Then comes decode. The instruction, which is just a pattern of bits, is sent to the control unit. The CU decodes it, meaning it interprets the pattern to figure out what operation needs to be done and what data is involved. Is it an addition, a memory access? It figures that out.
Okay, understand the command.
Exactly. After decode comes execute. This is where the operation is actually performed. The CU sends signals to the appropriate component, usually the ALU, maybe accessing data held in registers.
Right.
Now, depending on the instruction, there might be a couple more optional steps. There might be a memory access step if the instruction needs to read data from main memory or write data back out to it.
Makes sense if the data isn't in a register.
Precisely. And then there might be a write-back step where the result of the execution, say from ALU, is stored back into a register.
Okay.
And then the cycle repeats. Fetch the next instruction pointed to by the PC, decode, execute, maybe memory access, maybe write back, over and over, incredibly fast.
And that speed is tied to the clock speed, the gigahertz number we always hear about.
It is, yes. Clock speed in gigahertz tells you how many cycles the CPU can potentially start per second, billions. But, and this is really important, performance isn't just clock speed.
Yeah.
No. It's also about how much useful work gets done in each cycle. And it depends heavily on techniques like pipelining, which allows multiple instructions to be processed at different stages of the cycle simultaneously. We can get into that more later. A faster clock doesn't help much if the CPU stalls constantly or doesn't do much per tick.
Okay, that's a key point. Now, you've mentioned memory quite a bit. Our sources really emphasize something called the memory hierarchy.
Yeah.
Why is organizing memory in these different levels so important for performance?
The memory hierarchy. It's absolutely critical. The basic problem is a huge mismatch in speed. CPUs are incredibly fast, they can process data in nanoseconds, but main memory, RAM, is much, much slower.
A bottleneck, then.
A massive potential bottleneck, exactly. If the super fast CPU had to wait for slow RAM every single time it needed data or an instruction, the whole system would grind to a halt, relatively speaking. It wouldn't matter how fast the CPU could be.
Like having a Ferrari stuck in city traffic.
Perfect analogy. So the memory hierarchy is the solution. It's a tiered structure of different kinds of memory, arranged by speed, cost, and size, designed to bridge that speed gap. It works by exploiting a principle called locality. Locality of reference. It basically means programs tend to reuse data and instructions they've used recently. That's temporal locality. And they also tend to access data located near memory locations they just accessed. That's spatial locality.
So the hierarchy tries to predict what the CPU will need soon and keeps it in faster memory closer by.
That's the core idea, yes. Keep the most frequently and recently used stuff in the fastest, smallest, most expensive levels of memory, which are closest to the CPU. This minimizes the number of times the CPU has to make that slow trip out to main memory.
Okay, that makes sense. So what are these different levels? Can you walk us through them, starting closest to the CPU?
Sure. Think of it like a pyramid. At the very top, the absolute fastest level are the registers we already talked about.
Right, inside the CPU.
Exactly. Tiny capacity, maybe kilobytes, but access times are negligible, fractions of a clock cycle. They hold the data the CPU is immediately working on.
The CPU's workbench. What's just below that?
Next down is cache memory. This is really important. It's made of faster, more expensive memory called SRAM, static RAM. It's usually located right on the CPU chip or very close. Cache acts as a buffer, holding copies of data and instructions recently fetched from the slower main memory.
And there are different levels of cache too, right? L1, L2.
Yes, typically multiple levels. L1 cache is the smallest, maybe tens of kilobytes per core, but it's the fastest cache. It's often split into separate caches for instructions and data. Then there's L2 cache, larger, hundreds of kilobytes, maybe megabytes, and a bit slower than L1, often still private to each CPU core.
Okay.
And then often an L3 cache, which is larger still, several megabytes, maybe tens of megabytes, and slower than L1, L2, but still much, much faster than RAM. L3 is usually shared among all the cores on the chip.
So, like, increasingly larger, slightly slower waiting rooms for data the CPU might need.
That's a great way to put it. When the CPU needs something, it checks L1 first. If it's there, a cache hit, great, super fast.
And if not, a cache miss.
If it's a miss in L1, it checks L2. Miss again, check L3. If it's not in any cache level, then the CPU has to go all the way out to main memory, RAM, which takes significantly longer.
And that delay hurts performance.
Big time. That's why having a high cache hit rate, finding what you need in the cache most of the time, is absolutely crucial for keeping the CPU fed and running fast. When data is fetched from RAM, it's usually copied into the caches on the assumption it might be needed again soon, leveraging that locality principle.
Okay, so registers, then L1, L2, L3 cache. Below the cache is main memory, RAM.
Correct. Main memory, usually DRAM, dynamic RAM. This is where your operating system lives, you're running applications, the data they're actively using. Much larger capacity, gigabytes typically, but significantly slower access times than cache. And its volatile data disappears when the power goes off.
Right. And then for long-term storage, things we want to keep.
That's secondary storage. Non-volatile, keeps data without power, much slower access than RAM, but huge capacities. Terabytes now are common. In 2025, this is dominated by SSDs, solid-state drives.
Faster than the old spinning disks.
Much faster, yeah. They use flash memory. More durable, too. You still see HDDs, hard disk drives, the spinning magnetic ones, especially where very large capacity at low cost is needed. But SSDs are standard for most systems now, for the OS and applications.
And there's even slower storage beyond that.
Yep, tertiary or offline storage. Think backup tapes, archival systems, very large capacity, very low cost per gigabyte, but access is extremely slow, often needs manual intervention. So that whole pyramid, registers down to tape, is the memory hierarchy designed to balance speed, cost, and capacity.
Fascinating how it's all layered to work around those speed differences. Okay, let's shift gears slightly. Instruction set architecture, IS. You called it the hardware-software contract. Can you unpack that term? What does it really mean?
Yeah, the ISA is a really core concept. It's essentially the vocabulary the CPU understands. It defines every single instruction that a specific processor or family of processors can execute.
Like its command list.
Exactly. It's the complete specification of how software can talk to the hardware. That's why it's called the contract. The hardware promises to understand and execute instructions defined in the ISA, and the software promises to only use instructions from that ISA.
And what kinds of things does this contract specify?
It specifies the actual instructions, the opcodes for things like arithmetic, moving data, controlling program flow. It defines the registers that software can use, the different types of data the CPU can handle, integers, floating point numbers, maybe vectors. It also specifies how memory locations are addressed, the addressing modes, and the mechanisms for input and output. It's the complete programmer-visible interface to the hardware.
So this is why you can't just run, say, a Windows program compiled for an Intel chip on an ARM-based phone.
Precisely. They have different ISAs. Intel AMD mostly used by 8664. Most phones and many laptops now use ARM. They speak fundamentally different machine languages. The binary code for one is just meaningless noise to the other. Software has to be compiled or translated specifically for the target ISA. That contract is strict.
Our sources mention two main philosophies behind ISA design: CISC and RISC. What's the difference there?
Right. CISC and RISC, two different approaches to designing that instruction set. CISC stands for Complex Instruction Set Computer.
Complex.
Yeah. The idea here historically was to have a large number of instructions, including some very powerful complex ones that could perform multiple steps in a single command. Like load data from memory, add it to a register, and store the result back to memory all in one instruction.
Why do that?
The thinking was it might make compiler writing easier and potentially reduce the number of instructions needed for a given task, maybe saving memory, which used to be very expensive. The classic example of CISC is the by 8664 architecture used by Intel and AMD.
Okay, so CISC is about powerful multi-step instructions. What about RISC?
RISC is Reduced Instruction Set Computer. It takes the opposite approach. RISC philosophy favors a much smaller set of simple, highly optimized instructions.
Reduced set, simpler instructions.
Exactly. Each instruction does one simple thing, like load data, store data, perform an arithmetic operation. And crucially, these simple instructions are designed to be executed very quickly, ideally in a single clock cycle, and easily pipelined.
So how do you do complex things then?
You rely on smart compilers to break down complex operations into sequences of these simple RISC instructions. The benefits are often simpler hardware design, which can mean lower power consumption, potentially higher clock speeds because the simple instructions run faster, and generally better energy efficiency.
Which is great for phones and laptops.
Absolutely. ARM is the prime example of a successful RISC architecture. MIPS was another, and now we're seeing a lot of interest in RISC-V, which is an open standard RISC ISA gaining traction in 2025.
So kind of like CISC gives you complex tools, RISC gives you simple, fast building blocks.
That's a pretty good way to think about it, yeah. Both approaches have proven successful in different domains.
Okay, we've got the basics. CPU parts, memory, the ISA contract. Now let's talk about squeezing out more performance. You mentioned clock speed isn't everything. Our materials list several performance enhancement techniques. Let's start with pipelining. How does that speed things up?
Pipelining is fundamental to modern processor performance. Think of executing an instruction as a multi-step process. Fetch, decode, execute, memory access, write back, like we discussed.
Right, the instruction cycle stages.
Instead of doing all stages for one instruction before starting the next, pipelining works like an assembly line. It breaks the instruction execution path into these stages and allows different instructions to be in different stages at the same time.
Overlapping them.
Exactly. While one instruction is in the execute stage, the next one can be in the decode stage, and the one after that can be in the fetch stage. They all move down the pipeline simultaneously.
Ah, I see. So even if one instruction still takes, say, 5 clock cycles to complete its journey through the pipeline.
A new instruction can finish potentially every single clock cycle once the pipeline is full. It doesn't reduce the latency of a single instruction, but it dramatically increases the throughput, the rate at which instructions are completed. More work done per unit time.
That makes sense, like an assembly line getting more cars off the end per hour, even if each car takes the same total time to build. Are there downsides or challenges?
Oh yes, pipelines aren't perfect. Things called hazards can disrupt the flow. For instance, a data hazard occurs if an instruction needs the result of a previous instruction that hasn't finished moving through the pipeline yet.
It has to wait.
It might have to stall, yeah. Pause the pipeline. Or architects use clever tricks like forwarding, where a result is passed directly from one stage back to an earlier stage for the next instruction, bypassing some delay. Another big one is control hazards caused by branches.
Branches. Like if statements.
Exactly. When the CPU hits a branch, it doesn't know which path to take, the if path or the else path, until the condition is evaluated. This could force the pipeline to wait. That's where branch prediction comes in.
Okay, let's jump to that then. How does branch prediction help keep the pipeline moving?
So instead of waiting, the branch predictor makes an educated guess about which way the branch will go. Will the condition be true or false? Based on past behavior, usually.
It guesses.
It guesses, yeah. Sophisticated guessing. And then it speculatively starts fetching and executing instructions down the predicted path before the condition is actually known.
What if it guesses right?
If it guesses right, great. No stall. The pipeline keeps flowing smoothly, saving time.
And if it guesses wrong?
If it guesses wrong, there's a penalty. The pipeline has to be flushed, discard the wrong path instructions, and then fetch and start executing instructions from the correct path. This wastes cycles. But modern branch predictors are incredibly accurate, often well over 90%, sometimes 95% plus.
So the benefit of guessing right most of the time outweighs the penalty of guessing wrong occasionally.
Absolutely. It's a huge performance win overall, essential for high-performance CPUs.
Okay, very clever. Now, what about superscalar execution and out-of-order execution? More performance tricks.
Yes, building on pipelining. Superscalar execution means the processor has multiple execution units, maybe 2 ALUs, a separate unit for multiplication, etc. This allows it to fetch, decode, and actually execute more than one instruction in the same clock cycle, provided those instructions are independent.
So multiple pipelines or wider pipelines.
Kind of like having multiple parallel execution resources within a single core. If you have 2 independent add instructions ready, a superscalar processor might execute both simultaneously.
Doing more per clock tick? And out-of-order execution. That sounds counterintuitive.
It does, but it's another major performance booster. With UI, the processor can look ahead in the instruction stream and execute instructions not necessarily in the order they appear in the program.
Why would it do that?
To keep its execution units busy. Imagine instruction A needs data from slow memory, and it's going to take a while. Instruction B comes after A but is ready to go immediately. An UI processor can execute B before A finishes, even though B comes later in the code.
So it rearranges things on the fly to avoid waiting.
Exactly. It finds instructions that are ready and executes them, keeping the hardware busy, hiding the latency of slow operations like memory access. Crucially, though, the processor has complex logic to track dependencies and ensure that the final results are as if the instructions executed in the original program order. Correctness is always maintained.
Wow. That sounds incredibly complex internally.
It is. Modern high-performance CPUs are marvels of engineering, managing all this parallelism and reordering.
Okay, these techniques focus on making a single core faster.
Yep.
What about multi-core processors? How does putting multiple cores on one chip help?
Multi-core is about a different kind of parallelism, thread-level parallelism, or TLP. Instead of just trying to make one core do more things faster internally, that's instruction-level parallelism, ILP, which pipelining superscalar address, multi-core puts multiple complete independent processing cores onto a single chip.
Like having multiple CPUs in one package.
Essentially, yes. Each core can run a separate program, or more commonly, a separate thread of execution from the same program, truly simultaneously. This became the main way to increase performance over the last, say, 15 years or so, because pushing single core clock speeds much higher hit the power wall.
The power wall.
Yeah, running single cores faster and faster generated too much heat and used too much power. It became unsustainable. So the industry shifted strategy. Keep individual core speeds more modest, but put more cores on the chip. This allows a system to handle more tasks at once or run specially written parallel software much faster. Most processors in 2025, from phones to servers, are multi-core.
Makes sense. Spreading the work across multiple workers instead of making one worker impossibly fast. Now, another acronym, CMD. What's that about?
CMD stands for single instruction, multiple data. It's another form of parallelism, but focused on data. SIMD instructions allow the processor to perform the same operation on multiple pieces of data simultaneously.
How does that work?
CPUs with SIMD capabilities have wide registers that can hold multiple data elements, like maybe 4 or 8 integers, or several floating point numbers and special instructions that operate on all those elements in one go. So a single SIMD add instruction might add 4 pairs of numbers all at once.
Where would that be useful?
It's extremely useful for tasks with high data parallelism. Think multimedia processing, like adjusting the brightness of all pixels in an image, or processing audio samples, scientific computing with large vectors or matrices. And very importantly today, AI and machine learning often involve massive operations on large data sets that map really well to SIMD. It's about efficiency for repetitive operations on bulk data.
Got it. Doing the same thing to lots of data points at the same time. Okay, one more performance area. Hardware accelerators. What are they and why are they so important now?
Hardware accelerators are specialized pieces of hardware designed to do specific tasks much faster or more power efficiently than a general-purpose CPU could.
So not a CPU, but something else on the chip or system.
Exactly. As CPU performance scaling from just making CPUs faster has slowed, and as certain workloads have become incredibly demanding, think graphics, AI accelerators have become crucial. They offload specific jobs from the CPU.
What are some examples?
The most well-known is the GPU, the graphics processing unit. Originally for graphics, obviously, but their massively parallel structure makes them fantastic for general-purpose computing on parallel problems, GPU, scientific simulation, and especially AI training and inference.
Right, GPUs are huge in AI now.
Huge. And then you have even more specialized accelerators like TPUs, tensor processing units, developed by Google, or NPUs, neural processing units, appearing in many systems. These are ASICs, application-specific integrated circuits, designed specifically for the types of calculations common in machine learning, like matrix math. They can be much faster and use less power for those specific tasks than even a GPU.
So the trend is towards systems with a CPU plus various specialized accelerators working together.
Definitely. That's called heterogeneous computing, and it's a major trend in 2025 architecture, using the right tool for the job, basically.
Okay, this ties into modern trends. Looking at 2025, what are the key forces shaping computer architecture right now?
Well, we've touched on some already. The power wall is still a huge factor, driving the focus towards parallelism, multi-core, and especially energy efficiency. You can't just keep cranking up clock speeds.
Energy efficiency is key, especially for mobile.
Critical. And for data centers, too, frankly. That's partly behind the rise of ARM, even in servers. Another major trend is that rise of specialization, domain-specific architectures, or DSAs. That's the accelerators we just talked about. GPUs, TPUs, NPUs, maybe others for networking or video processing, augmenting or even sometimes replacing general-purpose CPUs for specific workloads.
What else is big right now?
Hardware security is a massive focus. Attacks like Spectre and Meltdown, which exploited aspects of modern processor design like speculative execution, really highlighted the need to build security features deeper into the hardware itself. Things like secure enclaves for sensitive data, memory encryption technologies. Architects are spending a lot more time thinking about security from the ground up.
That's really important. Any other major trends?
The rise of open architectures, particularly RASCV, is significant. Being an open standard, it offers flexibility, avoids licensing fees associated with ISAs like by86 or ARM, and allows companies to customize processors for specific needs. We're seeing growing adoption, especially in embedded systems, specialized accelerators, and potentially broader markets.
So efficiency, specialization, security, and openness seem to be key themes.
I think those capture the big movements in 2025, yes.
This has been incredibly illuminating. To sort of wrap things up, how would you summarize the fundamental role of computer architecture today?
I go back to that idea of the blueprint. Computer architecture is the fundamental discipline that connects the world of software, the algorithms, the applications, to the physical reality of hardware. It defines how processors are built, how memory is managed, how they communicate, the very language they speak.
The bridge between ideas and silicon.
Exactly. The core concepts, CPU design, the memory hierarchy, the ISA, and all the performance techniques like pipelining, parallelism, acceleration, they all work together to enable everything we do with computers. Understanding it, even at a basic level, gives you insight into why technology works the way it does, its capabilities, and its limitations.
And its future.
And its future. Continued innovation in architecture, tackling power, boosting parallelism, designing smarter accelerators, building in security is absolutely essential for progress in AI, scientific discovery, communication, everything. It really is the indispensable foundation of our digital age here in Canada and everywhere else in 2025.
Well, that's a perfect place to conclude our deep dive. Thank you so much for breaking down such a complex topic into something understandable.
My pleasure. It's a fascinating field, always evolving.
It really is. And listening to all this, it makes you think, with hardware becoming so specialized, GPUs for this, TPUs for that, how might that change the game for software developers? Will we see more software needing to be explicitly designed for specific hardware accelerators to get the best performance? What skills will be most in demand? Definitely some food for thought there.
Absolutely. The interaction is constantly shifting.
Well, thank you, everyone, for joining us today. If you found this exploration of computer architecture valuable, please do consider subscribing to our channel. It really helps us grow and bring you more deep dives like this one.
Thanks for listening.
We look forward to our next deep dive with you.